Hello everybody. In continuation with the V model explanation, I'm going to explain you one ADAS functionality development using the V model, which is lane departure warning. Lane departure warning is a very important ADAS functionality. Nowadays, more and more OEMs are implementing this particular functionality into their vehicle. So I will just, for an example, explain you clearly, methodically, step by step, the development of lane departure warning functionality using a V model. Okay, here I go. First of all, let's have a brief overview of LDW. I will be addressing lane departure warning as LDW. LDW is the V model. The V model basically consists of left side, which is the requirements, system design and component development, and the right side, which is integration and validation. Testing at the each level to ensure the compliance. Okay, so the integration validation, which I informed in the previous video, each and every step there will be a test to ensure the compliance. Now, what are the key request stages in LDW development? First is requirements definition, system design, software and hardware development, unit testing, integration testing, system validation, production and deployment. These are the major steps. Of course, these 7 steps have further sub steps, but for sake of explanation, so that you can have a clear cut bird's eye view about the LDW, I have limited these things to 7 steps. Now, detailed phases of LDW development. Let's start from the top left. The first requirement is requirements definition. Define what the LDW system must achieve. Okay. Now, what are the functional requirements? What are the main requirements of the LDW? It must wait a minute. I will just take a pointer so that you people can understand. Detect lane markings using camera, warn the driver either visually, haptically or auditory alerts if the vehicle unintentionally drifts out of the lane. Now I clearly explained you. Now I am explaining this under the assumption that all of you know what is LDW. I am explaining this under the assumption that all of you know what is meant by lane departure warning, as I explained in the beginning itself. So next important functional requirement is adjust sensitivity based on the vehicle speed. So just for example, let's say this lane departure warning should be invoked or activated only above 60 km per hour. Next is safety requirements. Safety requirements are based on the ISO 262. So safety requirements are no false positives, fail safe behavior. For example, disable LDW if camera fails, because LDW basically relies on the camera. Camera is the main sensor for LDW. Next, some regulatory requirements, whether it is a Euro NCAP scoring, must work in daylight and moderate rain. Now this is a NCAP requirement. Okay, European NCAP requirement, and again this daylight has some candela units. For example, it should go work above so many candela, or it should work under so many centimeters of rain. So all these requirements are also clearly outlined. Now next is performance requirements. Detection accuracy greater than or equal to 95% in clear lane marking, latency less than 100 milliseconds from detection to warning. Now this latency is very important, because smaller the latency, better the real time working condition. All right. Now next is the output. What is output? System requirement specification. So based on all these requirements definition, the output of this particular phase is system requirement specification document. Now this document is the document which is given to the next phase, which is system design. Okay. In this system design, you clearly explain how LDW will work at the system level. First is sensor selection. You select the sensor. Now depending upon your budget, depending upon your OEM requirement, you select whether monocular sensor or a stereo sensor. Again, I assume you know what is meant by monocular and stereo, as I explained in the sensors section. Whether it is this is again an optional requirement, whether the fusion with the GPS map data is required for the curved roads, and but this is optional. This is not exactly required for LEW, but it can be embedded into the requirement if particular OEM thinks it is required. Next is algorithm breakdown. What is algorithm breakdown? First you should perceive, then you should decisively logic, and next it is actuation. Okay, so lane detection marking have some particular perception software like how transform or deep learning, and next is decision learning. Example, no turn signal activated. Now as I said in the video about lane departure warning, only when turn signal is not activated, this lane departure warning algorithm is invoked. So this decision logic is also very important. Next is actuation. It clearly triggers the warning. Steering wheel vibration, dashboard icon, all these things are extremely important. ECU design. Now when you say ECU, it involves both the hardware and the software. It must be dedicated ADAS ECU or integrated domain controller. Now as more and more vehicles are moving towards centralized architecture or zonal architecture, whether you are having a dedicated ECU or many ADAS functionalities are going embedded into ECU, which has other requirement also, that needs to be finalized. And of course interfaces with CAN FlexRay for vehicle dynamics. So these are actual communication protocols. So the vehicle should have a clear cut outlined requirement with what are all communication protocols this particular ECU is going to interface. All right, now these are all the various requirements in the system design, and the output of this system design is system design document, which clearly ensures data flow diagrams, ECU architecture and sensor specs. Okay, now let's see, after the system design is completed, what happens next. This document is handed over to software and hardware development teams. Okay, now the previous in the previous slide we discussed about perception, decision logic and warning system, but they are high level requirements. In this next slide we are going to touch upon the lower level requirements, where pre-processed camera images, ROI based on ROI selection, denoising, all these are clearly implemented so that the camera images are pre-processed. And next is detect lane warning. This detection lane markings can be detected with the help of traditional computer vision or CNN. CNN stands for convolutional neural network based like lane net. All right, next comes the decision logic. Calculate the lateral offset from the lane center. Now this is extremely important, calculating the okay, let me briefly draw the drawing to you. For example, this is the road and this is the lane, a dotted lane. Okay, drawing is not exactly accurate, but I am sure you will understand. For example, this is your car which is going in this direction. So, and this is the center line of the car. This is called the offset. So based on this offset eccentricity, the decision will come to the picture. I mean, how close it should be to the lane before this lane departure warning begins to warn the driver. Okay, there is no point warning when it is quite a safe distance from the lane. It is only when this vehicle comes closer to the lane, when these left hand wheels, this wheel and this wheel comes very close to the vehicle, then this lane departure warning will begin to get invoked and activated. Okay, next comes the hardware development, camera calibration, ECU firmware development, which involves the real-time operating system, which involves the auto source stack. All these things are a part of the hardware development. Okay, next is, what is the output of the software and hardware development? Output is the actual code and also the actual camera module and the ECU. What are the specifications of the camera module? Okay, for example, what is the resolution rate, what is the FPS of the camera, whether it is a stereotype camera or a monocular camera, which brand the camera should come from, Bosch or Continental or Aptiv or any other camera manufacturer, and what again this ECU also. In this particular phase, this ECU specifications also finalized, including the brand of the ECU, whether this ECU is coming from NXP or Infineon or Texas Instruments, and what are all the various RAM specifications, ROM specifications. All these things are clearly identified in this particular phase. Now let's see the next phase. Next phase, this is now we have come to the right side of the V model, which and here it's the testing is begun. The unit testing, verify individual software and hardware components. And how do you do that? How do you verify an individual software component? With the help of software unit testing, MIL/SIL. Now I am going to slightly breeze through this, slightly rush up through this, because I have very clearly explained to you what is MIL and SIL in the concerned chapter. Okay, next comes the hardware unit testing, the validate camera frame rate, resolution, low light performance, and also the test ECU response time. Now for what are you testing the ECU? For the latency. As I said, lesser the latency, the more real time operating condition. For example, here it is 100 milliseconds. Nowadays there are some ECUs which are already working on at the level of microseconds. And who knows, as the technology further develops, the latency can further come down to nanosecond also. Okay, so the latency, lesser the latency, better the real time operating condition, that you clearly note down. Next is the integration testing. Now once the various units are tested individually and their efficacy is clearly proved, then you combine the components and you test the entire combined system. Now this is called integration system. This is called the integration system. Now this is where the hardware in loop is nothing but the actual ECU, which comprises of both the software and also the ECU, and it is combinedly tested. And it is combinedly tested with the help of some rigs like DSpace rigs. Next comes the vehicle level integration. Now test the actual LDW with real camera in controlled environment. Test track lane with lane markings. Check CAN bus communication, speed, turn signal data, and integration test logs, bug reports. All these things are very clearly outlined, or these are the actual outputs of this particular integration testing and also the unit testing. Unit test also has, as I mentioned here, unit test reports, code coverage metrics. All these things are output of the unit testing. Now once the unit testing and integration testing is completed, then we come to the system validation. In the system validation, the LDW, you ensure that it meets all the requirements in the real world conditions. Now this word is important, real world conditions. Okay, and in the system validation, again you have some tests like straight roads, curves, low contrast lanes, whether to ensure that all the NCAP scenarios are mentioned. All the NCAP scenarios are covered, that is ensured here, and all these NCAP scenarios include straight roads, curves, and low contrast lanes. What is this low contrast lane? This is where the actual accuracy of the camera comes into picture. If it is how effectively it can derive the lane even when the lane is slightly faded. Okay, once the lane is painted on the road, over the period of time the lane may get slightly faded. Even if it is faded, the camera should be able to identify the lane. That is the actual NCAP requirement. Next is the edge cases, whether it is a faded lane marking, construction zones, all these things are tested. That is the part of the as a part of the functional testing. Okay, next comes the safety validation. Safety validation, which is in line with ISO 26262. As I said, ISO 26262 I clearly explained to you in the functional safety chapter. The functional tests are there. Functional injection tests like camera occlusion, ECU fault injection test, ECU failure. What is meant by fault injection test? The whole system should be able to work even with a minute fault. So you deliberately inject a fault to see how the exact entire vehicle is working with the presence of the fault. That is called fault injection test. Now this is also something I already explained. And verify no false alarm during intentional lane changes. Now this is very important. If you are intentionally changing the lane, how does the computer know you are intentionally changing the lane? How does it know? Because the driver, he presses the signal that he is going to the next lane. So once the signal is pressed that he is going to the adjacent lane, then no alarm is required, because the computer or the vehicle understands that the driver is deliberately changing the lane. Okay, next is real world driving tests. Some OEMs, they uh, even though despite so much of simulation, some OEMs, they always rely on the real world test. Actually, there are some OEMs who go to countries like Sweden or Norway where there is heavy snow. There are some countries, OEMs, which go to very hot places like very hot cities like Jaipur in Rajasthan, so that the glare of the sunlight does not affect the lanes. So all these real world driving tests are also done by the OEMs. Okay. Now with this the validation report, the compliance certificates or output. These are the actual output of this final phase. Next comes the production and deployment. Okay. Now this is a very important phase, or rather this is the most important phase, because it is in this phase that you actually release the LDW to the market and monitor the performance. Here you ensure the camera and ECU production line testing are happening. You improve the algorithms based on the field data. Now after you release the ADAS functionality into the market, you ensure based on the field data, you clearly judge and monitor how efficiently this particular algorithm or particular functionality is working in the actual world. And based on that, through the over the air, you further enhance the software. Now what is meant by field monitoring? Field monitoring is nothing but correct the real world performance metrics. Okay, based on the feedback from the actual driver, the real world field monitoring is completed. And what is the output? Once this production and development phase is completed, then you are 100% sure that it is production ready and it is handed over to the production department. Till now, it is this all the 7 phases which I mentioned, they come under prototyping. It is only after the phase 7 the actual production and deployment comes into picture. Now what are the key tools used in LDW development? Okay, for requirements you use DOORS or Polarium. I'll be very honest with you, this JAMA Connect is a very modern tool. I am not exactly very sure where it is used, but DOORS and Polarium are very extensively used. Next is system design. System design, MATLAB, Simulink, SysML, these are the tools with the help of which the system is designed. Next comes the perception algorithms, where tools like PyTorch, TensorFlow, OpenCV are used. Next is unit testing, VectorCast, Google Test, hill testing, DSpace. Especially these DSpace rigs are very famous. In second place are ETAS, but most of the OEMs are unanimously buying these DSpace rigs for hill testing. Next comes the validation. Carla, Prescan and Pro Civic. These are the various types of validation tools, and some more validation tools like CarSim and CarMaker are also used. Okay. Next, what are the main challenges in LDW deployment? The main biggest challenge is handling the poor visibility. Now this is where what I said, and this is exactly why many OEMs, they take the cars to some remote places, some extreme temperature places to test the efficacy of the functionality. Adaptive algorithms for different road types. So for example, you develop an algorithm for a highway. Will the same algorithm be useful for urban road? This is the main challenge. Next is false alarm depression, distinguishing intentional lane changes from unintentional drifts. Next is meeting strict latency requirements, safety compliance, ASIL B or higher or fault tolerance. See, the reason why I mentioned ASIL B is because it is not exactly a life-threatening failure. If at all this functionality fails, it is not exactly life-threatening. That's the reason ASIL B should suffice. Now, we just to give you a workflow of the LDW. Camera captures the road image, it pre-processes. Next, with the help of perception software, the lane detection algorithm, it identifies the markings. Decision logic, is the vehicle drifting or is the turn signal off? With the help of decision logic, it decides whether the vehicle is drifting or the turn signal off, and then if the departure is detected, then it triggers the warning. And this trigger can happen in many ways, as I told you during the video about lane departure warning. It may be haptic, or it may be steering vibration, or it may be dashboard alert, it may be visual or audible beeps, or some kind of chimes. All these are the various ways in which the departure is detected. So in conclusion, the V model ensures LDW is developed methodically. Left side requirements, right side rigorous testing, and these approaches minimizes risks and ensure reliable, safe lane departure warnings compliant with the automotive standards. Okay, so this is how you develop a particular ADAS functionality step by step. Okay, now this 20 minutes I have covered extensively, but let me tell you, in the actual world, this whole thing may take quite a while. It may last from between 6 months to 8 months, depending upon the OEM requirements. Okay, but this, what I told just now, will definitely give you a clear idea about the flow of the work right from the scratch to the production. All right, thank you.